Hi, and welcome back to the FE exam review series where we focus on problems built around core fundamentals that will help you pass your FE exam. Today's problem is based off of the mathematics subject subsection C, ordinary differential equations, specifically Laplace transforms. I highly recommend you try the problem first before you watch this video solution, and you can do that using the first link in the description below. The FE exam is really all about practice, so getting in practice problems like these is getting you one step closer to passing the FE exam. I hope you tried the problem. Let's get into the solution. It says the function shown above is defined in the frequency domain. The value of its inverse Laplace transform at t equal to 0 is most nearly. Okay, so I transfer this to a clean sheet of paper here. And the first thing I'm going to do is just give a quick introduction on Laplace transform, give a quick refresher on why it's useful and how it can impact you for the FE exam. Now, the Laplace transform is a process that we use to take time domain functions and turn them into frequency domain functions, and we can do the inverse as well. So why this is useful is because when we have differential equations, let's say we have a time domain differential equation, what we could do is incorporate all the initial conditions and essentially transform that differential equation into an algebraic equation using Laplace transforms. So we have some function of time here. Let's say we have y's, y primes, and y double primes. We can take the Laplace transform and essentially end up with an algebraic equation for y as a function of s, or the frequency domain y function. We can isolate that y as a function of s and move everything other than the y as a function of s to the right-hand side, and we can end up with a function like this. Once we end up with this function, we can invert the Laplace transform to get our solution, or y as a function of t. So it's powerful because we can take differential equations and turn them into algebraic equations. Additionally, a lot of times in a subject like control systems, you can use it for stability analysis. So it's super useful for identifying these things called poles, which tell you something about the system stability. You can see this right-hand side term. If you have poles which are negative, you get decaying exponentials. Decaying exponential means stability. But if you have positive, that means that it'll be growing. You'll have positive exponentials. Your input-output relationship is one that is constantly growing. You also have these zeros, which is also useful. You can tell when a function, for what input, you'll have zero output. So that's kind of the big picture on Laplace transforms and why we kind of use it. Okay, so what about our problem? We have a frequency domain function. So our goal is to take it back to the time domain, and we're going to do that using an inverse Laplace transform. So the we're going to invert the frequency domain function f of s, and we're going to turn it into a time domain function, which is f of t. And we're going to evaluate f of t at t equal to 0 to get whatever the solution is. So that's going to be our general process. Usually when we're evaluating these Laplace transforms or inverse Laplace transforms, we refer back to a table. And you could find that table in the FE exam reference manual, page 56 of the 10-4 version of the FE reference manual. You can see the form of this table for these Laplace transform pairs. You'll have time domain functions on the left and frequency domain functions on the right-hand side. Going from time to frequency domain, you go from left to right, and you can inverse going from right to left. Now, what I'm looking for is something in the form of, I have something like this in the denominator. For our case, we have two cases like this. We have two like s plus a multiplied by s plus b. Now, our features aren't repeated like we're seeing here. And we have a linear term in the numerator, so none of these kind of look like what we have. There are certain techniques we can use to expand the usage of our tables, similar to what we did last week looking at use substitution, or we also spoke about integration by parts. Those techniques expand the use of integration tables, and a technique like partial fraction decomposition is one that you should be familiar with to expand the uses of these Laplace transform tables. Okay, So what I'm thinking is that we can utilize partial fraction decomposition to end up with two terms, like these exponential terms. We can then use this Laplace transform table to get our time domain function. And once we have that, we could evaluate it at t equal to 0. Okay, so in order to do the partial fraction decomposition, really all we're doing is taking this fraction and decomposing it into two separate fractions. We're going to write down the denominator here in terms of the factors that we see on the left-hand side. There's two linear distinct factors, s plus 1 and s plus 2. And all you need to do is make sure that you remember that the factor in the numerator is 1 less than the degree of the denominator. So if this is a linear factor, this will be a constant. So that's kind of what we have here. So we'll have two terms like this, and we can evaluate exactly what these a's and b's are using the technique of partial fraction decomposition. We're going to multiply both sides of this equation by s plus 1 times s plus 2. That will cancel out this term in the denominator of the left-hand side. So we'll have 3s plus 5, and that's going to be equal to a times s plus 2. You can see the s plus 1 is kind of canceled here when I multiplied, and the opposite happened on the b term. We end up with just the s plus 1. The s plus 2 will cancel. So this is our general form here, and we can use a system of equations here to solve for what a and b are, or we can plug in different s values to see what a and b are. Before we solve the rest of the problem, if you're enjoying this video and you're learning something, consider leaving a like and subscribing for more content like this. Additionally, if you're prepping for the FE Mechanical exam and looking for a resource that will help you pass, consider checking out my software, FE Interactive. It's the third link in the description below, and it'll give you access to multiple different sections, practice exams, review and improve sections, as well as a tips and tricks section, which helps you use your calculator better and save time on test day. An analytics page, which ties all of the different pages together. You get data for each of those pages, where you can view, for instance, how you did on each exam, as well as a detailed solution manual for each exam, so you know exactly where you're making the mistakes, what exactly is the misunderstanding coming from, and all of those are tied together with an overall data point. The overall data point can be reorganized in terms of performance so that you know what are my top three subjects, what are my bottom three subjects. Having this kind of data is super valuable since it helps you isolate your weaker points and fortify your strong ones. I'm confident that my software, FE Interactive, will help you pass the FE Mechanical exam. And again, you can check it out using the third link in the description below. Get 2 months of access for $29.99. Let's get back into the video. So plugging in different values is definitely the more easy way to do this. You can plug in s equal to -2. That'll make your a term 0. And if s is -2, 3 times -2, I'm looking at this term. 3 times -2 is -6 plus 5. That'll be -1 on the left-hand side. And if I plug in the -2 here, -2 and 1 makes -1. I have negative b here. What that means is b is equal to 1. What if I plug in s equal to -1? I plug that in to eliminate b. So I'll just end up with a if I plug in s equal to -1 here and s equal to -1 here. -3 and 5 makes 2. And -1 and 2 is 1. A is 2. Now that I know exactly what the frequency domain function is, I know that this function on the left-hand side, 3s plus 5 divided by these two factors, that's exactly equal to what I get when I plug in a equals to 2 over s plus 1 and b equal to 1 over s plus 2. Referring back to the Laplace transform tables, it is pretty clear that what we have is this. So all we need to do is take that a term, and we're essentially going to negate it and write it down as an exponential term to go from the frequency domain to time domain. So if we take the inverse Laplace transform of this function here, all we're going to do is write down the constant term, which is 2, e to the minus 1t plus 1e to the minus 2t. And this is our frequency domain function, f of t, that we could evaluate at t equal to 0 to get 2 plus 1. And that value is equal to 3. So the solution to this is going to be 3. We can go ahead and plug in that answer. And we did get it correct. We can view the explanation here. And what you could see is that all we did was understand that we had a Laplace transform, we had a frequency domain function, and we went ahead and took its inverse Laplace transform. We applied the technique of partial fraction decomposition, a technique that expanded the usage of our table and let us use that Laplace transform table. We wrote it down as two factors like this. We found A and B. So we had the time domain function. We had the frequency domain function that we took its inverse Laplace. And after we took its inverse Laplace, we had the time domain function that we evaluated at time t equal to 0 to get 3. If you enjoyed the video, consider leaving a like and subscribing. Thank you for watching. I'll see you in the next video. Goodbye.